Good afternoon or evening, y'all. We're going to start section 12.1 here with solids, and we're going to start with polyhedrons. And let's define what a polyhedron is. It's a solid. Forgot to push the button. Solid. That is bound by polygons. Okay, so what that means is that all of its sides, every side face is a polygon of some shape. It will be a polygon. And the vertex, a vertex of a polygon is a point where three or more edges meet. Okay, a point where three or more edges meet is going to be a vertex. So you can look at the picture over here and see that we have the polygons are faces. We have edges where the faces meet are edges. So I'm drawing them in red here. Those are all edges. And then we'll put in green these corners right here are all your vertices. Okay? So here's the type of solids that we have. Solids include either polyhedra, which are these, prisms and pyramids, where all the sides are polygons. And over here on the right, these are not polyhedron. And if you remember back to where we talked about what made a polygon, anything with a curved shape, such as the cone or the cylinder, was not a polygon. So then these are not polyhedra. Now we're still going to study them, and we're going to learn about their surface area and their volume, but they are not considered polyhedra. Okay, to classify solids, we classify solids by the bases that they have. We classify by the bases. And here what we need to know is that bases are the parallel sides when we're talking about a prism. So this prism here, we'll look at this prism over here on the left. This prism has two bases, and the bases are the shapes of a pentagon. So we call this one a pentagonal prism. A pentagonal prism. Okay, so a prism has rectangles for the sides. The top and the bottom here, top, and then the bottom down here are both pentagons. And then if you look at these sides, they join the vertices from the top pentagon to the bottom pentagon to the bases. It joins the top and the bottom here, these sides do. And so we create rectangles. So around a prism, when we connect the vertice from the top, I'm going to go to a different color. When we connect the vertice from the top down to the vertice at the bottom, and we do that with two consecutive vertices, we get a rectangular shape. Okay, so that's a pentagonal prism. And if we look at the picture here on the right, my base is this one right here that it's sitting on. That is a triangle. And so this is going to be a triangular pyramid. Okay, triangular pyramid. If you look at, we have a base here, and then the sides go from the base down here. Each of the vertices of the base we will bring up to a common point right here. Common point called a vertice. And so if you look at each of these sides, they are triangular shape. So the sides of this are all triangular shape. And we'll look at that a little bit more when we get into section 12.3. Okay, but let's look first down here at example 1 and telling whether or not this solid that we're looking at is a polyhedron. If it is, we're going to name it. Find the number of faces, vertices, and edges. So on A here, we do have a polyhedron, And this one is a rectangular prism. Okay, a rectangular prism. And my bases, on a rectangular prism, it's really kind of your choice. We can call the front here and the back the bases, and then the sides would be connected by, you connect vertices, and then it would have 1, 2, 3 faces around the outside. You can say that the side that it's sitting on is the base, and the top is a base, and then all the other sides are faces. So let's look at how many number of faces it has. So it has the one in the front, one in the back, top, and I'll put one right here for bottom, left side, and I'll put one over here for the right side. So we have 1, 2, 3, 4, 5, 6 sides, 6 faces. 6 faces. And then if we look at the vertices, let's go with red. We have 1, 2, 3, 4. On that back side, there's 4 vertices. And then at the other end here, we're going to have 1, 2, 3, 4 vertices also, where we connect the edges of the faces. I'm going to look at the front and the back being the bases. So I have 4 on each end. That's going to give me 8 vertices. And then edges. We'll go with green for edges. So around the front, 1, 2, 3, 4 edges. And you know we're going to have the same 4 edges on the back side there, same 4 edges. So I have 4 plus 4. So far I have 8. And then we're going to connect all the vertices. 1, 2, 3, and then the one in the back there would be 4. So 4 plus 4 plus 4 around is going to give me 12 edges. Okay, so that's how you count them up. On B, let's look at B. Is it a polyhedron? And yes, it is a polyhedron. It is a hexagonal. If you look at the bottom, it has 6 sides and then 3 on the other side. So this is a hexagonal. Sorry, it's hard to write with these styluses, but I'm doing the best I can. We've got a hexagonal, and then we come up to one point here, so this is a pyramid. Okay, hexagonal pyramid. And so if we look at this one, the number of faces, we have the face on the bottom. That's my hexagon, so we have a face on the bottom. And then at each vertice, we have a face here, so each side is going to have a face that goes up to a certain point. And so I am going to have 6 of these faces all the way around with each side of the pentagon or the hexagon that is the base that go up to a common point. So I'm going to have 6 sides all the way around, 6 faces, and plus the one on the bottom. And so I'm going to do B over here. So I'm going to have 7 faces. And then let's look at vertices. Well, if we go and look at around the base, I'm going to have every point here of the hexagon shape is going to have a vertex. So that's 6 vertices around it, and then we have the one vertex right up here where they meet. So we're going to have 7 vertices. And then let's go to green, and let's look at the number of edges. So edges again, the sides of the hexagon, when you go around it, there's going to be 6 of those sides, and then from each vertex, we're going to have an edge that goes up to the top. So each side, 2, 3, 4, 5, 6 vertices around. I'm sorry, not vertices, we're talking about edges. So we'll have 6 edges that go up to the vertice at the very top. 6 of those edges plus the 6 that are around the base is going to give me 12 edges. Okay? If we look at number C, is this a polyhedron? I gave you a second to think about it. No, it is not. It has curved shapes, so it is not a polyhedron. Okay, what we have now on this slide is called Euler's theorem. Looks like it should be Euler, but it's pronounced Euler. Euler's theorem has, this is the following theorem that he came up with. We've got faces plus vertices equals the number of edges plus 2. Faces plus vertices equals edges plus 2. So F is faces, V is for vertices, and edges, E is for edges. Okay, so let's look at this. Let's look at this formula and see what we get. On this construction, find the number of edges on the frame of the house. Well, let's look at this frame here and see what we have. Right there, and we go down here to this base. Nope, let's go back on that one. Okay, so let's look at the number of edges that we would have here. Around the bottom, there. Around the bottom we have 1, and I could do this one in red. Edges 1, 2, 3, and then 4 give me the base. And then at the top I'm also going to have those same 4 here. So far that's 8. We got the front and the back here, 9, 10, 11, and then 1 in the back here, 12. And then let's look at the roof. 13, 14, 15, 16, and 17 edges. Okay, but let's go back for a minute and take a look at this front side right here. If you're going to look at the front side all as one piece, then this right here will not be an edge. And this one back here will also not be an edge because that will be one flat piece. So my edges is actually 15 instead of 17. Let's check that theorem and see if we get the same thing then. Faces plus vertices equals edges plus 2. So faces plus vertices equals edges plus 2. So let's look at the number of faces. We're going to have 1 here on each side here, and then again on the back, 2, the side on the left, side on the right, 3, 4, here, 5, on the other side of the roof, 6, and then we can't forget the bottom, 7. So I have 7 faces. Let's look at the number of vertices. What haven't I used? Let's look at blue. So vertices, 1 here on the top, 2, 3, 4, 1 at the back there, 5, 6, 7, 8, 9, and 10 vertices. Equals the number of edges that we found. Well, actually, let's solve for that. That's what we're checking on. Can we solve for that? Edges plus 2. Edges is what we were looking for. So let's solve. 7 plus 10 is going to give me 17. Equals the number of edges plus 2. But now if I subtract that 2 from both sides, then I'm going to get the edges equals 15. Okay? Okay, let's think back to our polygons and think about for our regular polyhedral and what that will mean. It means that a polyhedron is regular if, sorry, I got too close to the edge, if all its faces are congruent, regular polygons. Okay, if all of its faces, all of them, every single one, is a regular congruent polygon, then we have a polyhedral. And these are our 5 regular polyhedra. And they are a regular tetrahedron, which has 4 faces that are all congruent triangles, a cube, 6 faces of congruent squares. A regular octahedron has 8 faces, all congruent triangles. A dodecahedron, 12 faces. Each one is a pentagon, a regular pentagon. And then an icosahedron has 20 faces, all congruent regular triangles. And those are our 5 regular polyhedra. Okay, if we look at Euler's theorem with Platonic solids, on this example down here, we're going to find the number of faces, vertices, and edges of the regular octahedron and check our answer using Euler's theorem. Okay, so let's look at how many faces would we have. Well, we're going to have 4 triangles, 1, 2, 3, 4 faces around the top, and then another 4 faces around the bottom. So I'm going to have 8 faces. Let's look at the number of vertices. I'm going to use red for vertices. I'm going to have 1 here. So around the middle, we're going to have 4 points where this top pyramid and the bottom pyramid basically meet. There's going to be 4 points around the edges, and then at the top and at the bottom there'll be another one. So that's going to be 6 vertices. And then let's look at the number of edges. Around the middle, 4 edges, right, around the middle. And then from those edges, at each vertex, we're going to have an edge that'll go up to the top. And so we'll have 4 of those around the top, and then another 4 of those around the bottom. So as far as edges goes, we're going to have 4 middle, 4 top, 4 bottom, so that's going to be 12 edges. Let's check it with Euler's theorem. Faces plus vertices, 8 plus 6, does that equal edges plus 2? And 8 plus 6 is 14, and so this side, 14, and then 12 plus 2, 14. So Euler's theorem is true here. Okay, a cross-section. A cross-section is an intersection of a plane and a solid. Okay, so basically we look at this as a little slice. We're taking this really thin little slice of a plane and we're gonna slice through a figure. And so really what we're looking at, what we're trying to get you to see here is what shape is going to be formed by that intersection, by that little sliver. If I take a little bitty tiny sliver out of this cube going diagonally, what kind of a shape will I see? And what I would get would be triangular. If I take a slice through a cone, that shape right here in the middle would be a circle. Nope. Or could possibly be elliptical in shape. But this looks like it's going to be from a cone, from a regular cone, which we'll study in a minute. That's going to be circular. And then if I take this slice with this plane through a hexagonal prism here, that shape is going to be the same as the base, and it would be a hexagon. All right, that's it. I'll see you on the next one.